All right, everyone, thank you for coming to class today. I know there's some issues on campus with the quarantine and stuff, but you guys still made it. This lecture is recorded for those of you that could not make it for whatever reason. So today is March 22nd. So make sure you have already turned in homework 15. I'll put in the points in. But now we've moved on to homework 16. So please start working on homework 16. Please start working on your quiz 3. All right, do not wait till the last moment. The quiz 3 is due the same day as the test. Whenever the test is, I think it's coming up soon. Anyone have the date? I can find out and tell you about it, but it's in a couple of weeks. I'm supposing it will be on chapters 15 and 16. Okay. And right now we're on chapter 16. Another thing I want you guys to do is the lab report on Le Chatelier's principle. So we had a better turnout last Friday. Okay, Robert. I'm glad you came, but you could have had more lab partners. So lab report on Le Chatelier's, it'll be due. We'll make it due this Friday. If you want more time, we can have it for next Friday, but I would prefer you turn it in this Friday. Turn in that lab report. And this Friday there is no lab, it's a problem set. So this Friday's lab is a problem set. It's a very extensive problem set. So work with your lab mates, lab group, bless you, and lab problem set. Okay, so no lab, it's a bunch of practice problems. All right, so work together, work with the group. I think I have the answer key uploaded. Check your answers. So really, really grind to get home. You know, these are the ultimate in drills. Okay, ultimate in drills, ultimate in your reps. This problem set, and that is this Friday, also next Friday as well. Yeah. I believe it's next Friday as well. I'm not sure. I'll check the syllabus, but definitely this Friday. There is no lab. Do the lab problem set. Make sure you still do your clutch prep. All right, I'll give you extra credit at the end of the semester, and then at the end of the semester, I will collect your lab notebook. Everyone is doing the labs just fine. We're happy about that, but we want you also to turn in your lab notebook at the end of the term. Anything else that I'm missing off the top of your head? Anything? Okay. All right, so let's talk about our new chapter here, chapter 16. Right, here are your homework problems. I think I have them also worked out on Canvas to help you if you come across any issues. So the first thing I want to teach you guys is something called the common ion effect. All right, so the common ion effect basically is this. Okay, this molecule is called acetic acid. And that is, remember, this is an acid. It's also a weak acid. Why is it weak? Because it's not part of our 6. Okay, so it's a weak acid. And acids do what acids do. They're going to deliver protons. This is Bronsted acids, Bronsted bases. Do not confuse with Lewis acids or Lewis bases. So the acid, acetic acid, will donate the proton to water, and then water becomes this. Okay, this is called the hydromonium ion, and this acetic acid becomes the acetate ion. So acetic acid is a weak acid, you guys remember, so that's going to have a Ka. We'll look it up in the book. I'll give you the Ka. And another thing here, hopefully you guys know this. Acetic acid is an acid, so please know this for the exam. It's the acid, and it gives rise to A minus acetate ion, which is the conjugate base. Okay, so here's the acid and the conjugate base. That's the pairing, and I pair them in red. Let's highlight in orange. You see this water, it picks up the proton. It picks it up, takes the proton, abstracts the proton. Okay, we're going to call that the base. And when it picks up that proton, Bronsted proton, it becomes this. Hydroammonium ion is the name of this species, and that is the conjugate acid. All right, so hopefully all of this is a review. Hopefully. So make sure you know you can identify these on an exam. Bless you. So what we're going to do now is we have this acetic acid solution. Okay, what we're going to do is I'm going to take some sodium acetate. I wish I brought some sodium acetate. I didn't. But I'm going to take some sodium acetate. You know, it's a white solid. Okay. And I'm going to put it in some water. Okay, sodium acetate dissolves in water. So now we have sodium acetate solution. Sodium acetate solution. It's dissolved in water, so actually it's an electrolyte. Okay, solution. The solute is sodium acetate. The solvent is water. Remember some of that? Okay, solute plus solvent. So sodium acetate in water. Okay, so I have this in a beaker. And what I'm going to do here, so try to visualize this with me. Okay, I'm going to dump it to this bottle of acetic acid. Okay, I'm going to dump it into this bottle of acetic acid. And one thing you'll notice here, you see sodium acetate in solution has acetate ion in it. It also has sodium ion, but it has acetate ion in it. What does this bottle of formic acid have? It also has acetate in it. Everyone kind of see that? You see acetic acid. Acetic acid is not a strong acid, so it's not this way. Somewhere it kind of balances out. So a bottle of acetic acid will have some acetate. Okay, I took some sodium acetate powder, put it in water. It's a solution, and I dump it in here. So this also has acetate in water. This acid has acetate in water. So what is my common ion? Okay, my common ion is acetate. So what happens is that when I add the sodium acetate solution into this acetic acid solution, okay, this is acetic acid, this is sodium acetate, join them together, and what happens is that the reaction is going to go this way. Okay, so you'll actually make more acetic acid. I think we saw this in your lab last Friday. Okay. So this is the shift in the equilibrium. Shift in equilibrium. Okay, because of the common ion. Okay, and in this example, the common ion is acetate, is it not? Okay, in this, my visual diagram, sodium acetate, we dump some sodium acetate, white powder, into water, it dissolves, dump it into this bottle of acetic acid. Acetic acid is the name of this substance. The equilibrium will go this way because of the common ion acetate. So the common ion effect, let me read this out for you guys. The common ion effect is a shift in the equilibrium caused by the addition of a compound having an ion in common with the dissolved substance. And the presence of the common ion suppresses the ionization of a weak acid or base. Okay, so this is very prophetic. Okay, suppresses, and that's what we see in this reaction. Let's push this above, suppression. Okay, we are not getting the ions acetate. We're not getting the ion acetate. We're not getting the ion H3O+. That's the suppression of the ionization. Instead, we're getting more water and more acetic acid. So in other words, the equilibrium will be shifted away from less ions. Less ions because of the common ion. So this is called the common ion effect. Okay, where do we see the common ion effect most profound for all the biology majors? Where's the common ion effect mostly used? In buffers. Okay, you see a buffer, as we will talk about. You see a buffer, as we will talk about more in this chapter. A buffer is a combination of the acid, so I'll call that the conjugate acid, with a little bit of the conjugate base. So if you have a bottle or a beaker or whatever container with the conjugate acid, here this is called acetic acid. And in that same bottle, you have the conjugate base, which is acetate. Let's say I have this in this beaker. Okay. I have basically a buffer. Okay. So what is a buffer? A buffer is something that resists changes in pH. We talked about pH in the last chapter. So it resists wild shifts or changes in pH. So it keeps the pH steady. Or you can also say POH, but everything is really pH in this world. pH. Everything's pH, pH, pH. Okay, so why does this keep the pH steady? Let's think about this for a moment. Common ion effect, we have acetic acid and acetate. We have some combination of conjugate acid and conjugate base. Okay, so we actually have a buffer set up here. But let's just think about this for a moment. Let's say I add base. Okay. Okay, let's say I add base. Okay. Who will neutralize the base? The weak acid. Okay. The weak acid will neutralize the base. So if we add OH minus, which is a base, will be neutralized or will be taken, attacked, whatever you want to call it, will be neutralized by the weak base, by the weak acid, by the weak acid, acetic acid. Okay, that's scenario 1. What about scenario 2? I add acid. Okay, here I'll add OH minus in the form of sodium hydroxide, aqueous. Here I'll add acid in the form of HCl, aqueous. Okay, if I add acid, okay, who's going to neutralize the strong acid? If not all of it, some of it. It's going to be the conjugate base. Okay. So will be neutralized by weak base acetate. Okay, acetate ion. That's the name of this chemical. So by adding the common ion, let's go back here briefly. By adding the common ion, we've actually created somewhat of a buffer. Okay, and a buffer can, you add OH minus base, the pH will go up. Not so, because here that OH minus will be, some of it will be sort of neutralized by the acid. Here we add HCl, strong acid, H+. We'd expect the pH to go down, but not really, because some of that H+ is going to be neutralized by the acetate. So in essence, the pH is not going to go all the way up, and it's not going to go all the way down, because the conjugate acid and conjugate base are going to sort of balance it. Okay, neutralize base if you add it, or neutralize acid if you add it. Once again, neutralize base or neutralize the acid. So that's how buffers work. All right, a lot more information on buffers. This is just something of a little bit of a teaser. All right, I want to introduce another equilibrium constant to you guys. So equilibrium constant is K. The very beginning of all of this equilibrium stuff, we talked about Kc, which stands for concentration. We talked about Kp. What does the P stand for? Pressure. Okay. We talked about Kw, which is for water. This has a value of 1.00 times 10 to the minus 14. We talked about Ka. Okay, those are for weak acids. We talked about Kb. Okay, those are for weak bases. All right, now let's inform ourselves about a new equilibrium constant, products over reactants, each raised to the coefficient, and that is called Ksp. All right, so Ksp stands for our new K here. Ksp stands for the solubility product constant. So all these different Ks we've learned, K, 1, 2, 3, 4, 5. Okay, so there's a sixth one here known as Ksp. It stands for the solubility product constant. So Ksp is used for a sparingly soluble solid. Adjust myself here. Sparingly soluble solid. Okay, so what is a sparingly soluble solid? Okay, here's an example right here, calcium fluoride. All right, you see here I have calcium fluoride that is at an equilibrium with calcium ion, aqueous, and fluoride ion, aqueous. Okay, don't forget the 2 here to balance the equation. All right, so is this equation balanced? The answer is yes. Let me ask you this, and this is going to become somewhat important. Okay, what's the charge on your reactant side? Is there any charge? No, so it's 0. What's the charge on the product side? +2. And what about this? Not -1. Because of the coefficient -2. Excellent. So what's -2 plus +2? 0. So you see this is also charge balanced. Okay, charge balanced, right? Everyone see that? Got to be charge balanced. As well as mass balanced, right? Mass balanced means 2F and 2F. So what is the KSP for this? Okay, notice not KW, not KA, not KB, not KP, okay? What is KSP? Products over reactants. Okay, what do we do with that calcium fluoride solid? Do we put it in? No. Okay, very good, Joshua, no. Where does this F minus get raised to? What power? 1? 2. A lot of people by accident miss this. It's very easy to miss. It's very, very easy to miss. I want to jump up and down and tell you guys, okay? Don't forget this. Okay, do we put divided by calcium fluoride? As Josh warned us, do not do that because it's a solid, right? Okay, I think someone put this in the last exam, I believe. Okay, solids don't go into the equilibrium constant. So this is it. This is the KSP. And it has some number. I can look it up. We can look it up for you. And I'll give you the KSP values. All right, what else do you see here? Remember, this is chemistry. We got to look at everything. It's like driving. When you're driving, you have 10 different things you're looking at. Okay, that means what? Back and forth. Back and forth basically means equilibrium. Yes. Okay. Okay, so it's going to settle, but that back and forth means this reaction is not 100% going. It's not 100% staying here, and it's definitely not 100% going to products, calcium ion and fluoride ion. Okay, it's going to settle. Here's our P for product. It's going to settle. Okay, maybe more product, maybe more solid, don't know. Okay, it all depends on this number. Okay, it all depends on this number. All right, so calcium fluoride is an example of a sparingly soluble solid. I think we did this in, let's see if I can get that. I think we did this in your lab. So let's see if we can try to recreate this. A little bit of a break. So I'll take some calcium nitrate for those that are watching. I'll just squirt some. I'm being very qualitative here, so I'm not worried about 5 mils, 6 mils. That would be quantitative. This is qualitative. So here is my calcium nitrate. Remember, all nitrates are soluble. Here is 6 molar. Okay, that's pretty concentrated. 6 molar sodium hydroxide. Calcium nitrate soluble, sodium hydroxide obviously soluble. Let's see what happens. Okay, we get calcium hydroxide. Okay, so here's the calcium hydroxide, those watching. All right, calcium hydroxide. Okay, it looks very white, very milky. You guys did this, and I think we even collected this, remember? I know you did. You made that filter paper. So nice. One of the best filter papers I've seen in a while. But seriously. All right, so calcium hydroxide is not just a precipitate, okay? It also belongs to the same category as calcium fluoride, in that it's a sparingly soluble precipitate. All right, so let me write for you that equation. So we have calcium hydroxide. Back and forth, it's a solid. Okay, you see this? It's a solid. All right. It's a solid. It's in an equilibrium with calcium ion. Calcium is +2, remember? Plus hydroxide ion. Okay. What do we need to do in front of the OH? Okay, right? We have to put a 2 in front of the OH, is it not so? Okay, to balance it. Always balance. All right, what is the KSP for this reaction? Products over reactants. Okay, so what's our product? Calcium ion. What's our other product? OH minus. What do we need to do with that OH minus? To power what number? 2. Very good. Okay, a lot of people miss this. Divided by calcium hydroxide? Yes or no? No, because it's a solid. Okay, very good. Okay. All right, so this is how we write our KSPs. Okay, it's just the same as we've done before with other Ks, except we have a solid. This is not 100% solid. I have to try to convince you. It's not 100% solid. Inside this little white gunk, okay, white mess, there's calcium ion and hydroxide ion. In fact, that back and forth arrow should tell us that Le Chatelier's principle is at work. It's at an equilibrium or back and forth. I'm going to try to make this go back and forth. And you guys did this, so. Okay, I'm going to take this precipitate here, and I'm going to add some OH minus. Okay, what's the common ion here if I add OH minus to the calcium hydroxide? Common ion is OH minus, very good. So what do you think would happen? More solid, right? So, I don't know if you see this. It's probably hard to, well, I know you guys can't see this, but well, you may think nothing is happening, but it is making more solid. Okay, it's getting more white. All right. Well, how about if I add more acid? What will it do? More liquid. Okay, 6 molar, that's pretty concentrated. You see, whatever the acid does, the base does opposite. Whatever the base does, the acid does opposite. So, if this should work, hopefully we believe in science, this strong acid should neutralize the OH minus. We remove the OH minus, what happens? The reaction is going to go this way. Okay, so here there is no common ion. H plus Cl minus, calcium ion, hydroxide, no common ion. But the H plus will neutralize this, taking away this. When you take away this, Le Chatelier's tells us it's going to go this way. So you're correct, Adriana. It should dissolve it or make it more liquid. Let's see if that happens. Okay. Yeah. Okay. Maybe hard to see, but it's dissolving. It actually is maybe a little hard to see. Huh?
It looks like it's going back to solid.
The solid is clumping up. Say that again?
I said ours in lab like had clumps on the bottom and then it turned clear.
Yeah, it's clearing up. I can always add more.
I was about to say you're not measuring it either, so it might.
It's called qualitative.
But I mean, like, don't you kind of have to double the chemicals every time because they even out in a sense?
Yeah. Especially with OH and H plus, they have to even out. The acids and bases must even out. That's correct. So see, okay,
Oh, no, it's clear.
it's clear definitely. So I can add OH minus. This is what Adriana was alluding to with the back and forth. Okay, I could add OH minus and make it go this way. Adding OH minus makes it go this way. Okay, so we'll do that. So yeah, equilibrium is all about back and forth. Okay, it's not going to settle 100% products, 100% reactants. Okay, here we go. For those watching online, I just added some more OH minus, and you can see I got it back. I can add HCl, strong acid, and get it back into liquid. Okay. So we did Le Chatelier's principle. We did Le Chatelier's principle, but we did it with a sparingly soluble solid. Okay, we did it with a sparingly soluble solid. We did it with a molecule that has a KSP. Okay, this is not 100% solid, neither is it 100% ions. Calcium ion or hydroxide ion. All right. Common ion effect, we add hydroxide ion, it goes this way. What happens if we add calcium ion? What happens if we add calcium nitrate? What will happen to this equilibrium if I add calcium ion, the common ion here? What will happen? You'll get more solid, right? If I add calcium ion in the form of calcium nitrate, remember, all nitrates are soluble, so it's calcium ion and nitrate ion. Elena's correct. I add calcium ion, I'm going to get more solid. Okay? So, common ion effect. All right, let me just show you this equation here. This is called the Henderson-Hasselbalch Equation. All right, these were two physiologists, and I think Hasselbalch is from Harvard. He was an actual doctor in Harvard Medical School, and he and Henderson came up with the Henderson-Hasselbalch Equation. They used it a lot in physiology. There's also something called Hasselbalch Hall at Harvard. Hasselbalch Hall is named after Hasselbalch from the Henderson-Hasselbalch equation. We use it here in Gen Chem 2 to talk about buffers. Okay. So the equation is this. I'll give you the equation, and I'm not going to derive it. I'm just giving it to you on the exam. It's very easy to derive. The pH of a buffer is going to equal to pKa plus, okay, everyone see this? I'll give you this on the test. But, if you're taking MCAT or whatever the exams, we may need to memorize it. pH is equal to pKa plus the log of this fraction, the conjugate base A minus divided by the conjugate acid HA. Okay. And that's the version I'll give you on the test. For those of you that want to memorize this, the pre-medical students, the PA students, biology majors, the way to memorize this fraction, pH is equal to pKa plus the log of, which goes in the denominator. The way you memorize that is you think to yourself, drop the acid. And when you say drop the acid, that means the HA acid goes in the denominator. So drop the acid. Okay, that's for those that want to memorize this. Okay. So if I memorize this, I always say to myself, drop the acid. Right, so pH is equal to pKa plus log A minus over HA. How do I know the HA acid goes in the denominator? Drop the acid. There's also a pOH version. I'm not going to teach that to you because once you get the pH, how do you get the pOH? Subtract 14. Okay, so there's also the pOH version of that, and it's a little bit different. pOH, you're using pKb and so on and so forth, but this is the one you'll use on any exam. All right, and it's best used for buffers. Okay, remember, what is a buffer? Okay, it has two components. It has A minus, the conjugate base, and it has HA, the conjugate acid. Okay, so use this for buffers. Use this for buffers. All right, so instead of using some ice tables and all that stuff, we like to make our lives a little bit easier. And that's what scientists are. I want you to recognize scientists, mathematicians, these people, math people, science people, very lazy. So in that sense, we always want to avoid doing any hard work, make our lives easier. So if you're given a problem here, calculate the pH of 0.2 molar acetic acid, well, we have to do our ice table here. I think I'll just end it in class today, and we'll do this on Wednesday. So in part A here, scientists are very lazy. That's with part B. But for part A, we're going to have to use the ice table. Come on. This thing's so. We're not in the same page, obviously. All right, part A here, we're going to have to use the ice table, calculate the pH of a 0.2 molar acetic acid. But part B, we don't have to use an ice table. This is what I was saying. Science people, math people, they can be very lazy. They can use, instead of the ice table, they could use the Henderson-Hasselbalch Equation. Okay. But before we do that, let's go to part A here. Calculate the pH of a 0.2 molar acetic acid solution. So for this, we have to write the equation. Okay, we have to know the Ka. I'll give you the Ka on the exam, but it's about 1.75 times 10 to the minus 5. Okay, so I'll give you that on the exam. Do not memorize this. Okay, and this is at 25 degrees. Okay. So now we have 0.2 molar. 0, 0, minus x, plus x, plus x. This is the ice table. 0.2 minus x plus x plus x. Okay, so why can I not use pH equals minus the log of H plus here? Okay, why can't I use that? Because it's not a strong acid. Okay, if it was our 6 strong acids, then we can put it into this. But it's not a strong acid, correct? Because it's not a strong acid, we have to use ice table. If it was something else, then yes. If it's one of our 6 strong acids, then yes, we can use that. Because it's a weak acid, with the Ka that is of this magnitude, we have to use the ice table here. All right, we'll plug this in. Ka is equal to H3O plus, acetate ion, divided by acetic acid. All right, so the Ka for here, again, I'll give that to you, is 1.75 times 10 to the minus 5. Okay, this H3O plus is X, this acetate ion is X. X times X is X squared, divided by 0.20 minus X. All right, we're going to assume X is small. So 0.2 minus X is 0.2. So 1.5 times 10 to the minus 5 is equal to X squared divided by 0.20. Okay, everyone with me so far? Ice tables assume X is small. This is called the low ionization assumption. So I'm going to skip a couple of steps here. 1.75 times 10 to the minus 5 times 0.2. I'm going to square root that all to isolate X. Right, 0.2 times this equals X squared. To get X, I square root that. Okay, so Alright, so here my value of X is equal to 3.5 times 10 to the minus 6 big M. Okay, here you want to put big M. And here that is X is equal to H3O plus. Also that X is equal to CH3COO minus. So pH is minus the log of H3O plus which is minus the log of 3.5 times 10 to the minus 6. pH does not have units. Okay,
What does the green say?
the green is pH is minus the log of H3O plus, the formula for pH. Yep. Yeah, green is probably not the best color. I could turn off the lights too. Yeah, it's just the formula. All right. Minus the log of 3.1. 5.45 is our pH. Remember, this has no units. All right, so, well, that is the answer for part A, okay? Standard ice table. The last 5 minutes of class is part B is what I'd like to focus our attention on. Calculate the pH when you have that same acetic acid, but now we have 0.3 molar of acetate. Okay, so now instead of doing the same ice table, you see I could do an ice table, 0.2 here, and then 0.3 here, and then figure out which way it goes. That can be a little bit of a hassle, but we can use the Henderson-Hasselbalch equation here. And that's what I was alluding to, okay? Be lazy, use the equation. If you can avoid the ice table, if you can avoid using the quadratic, use that, do that. So now we will answer part B with the Henderson-Hasselbalch equation, and then we will end our class for today. Right, here's our Henderson-Hasselbalch equation. Remember, once again, it's utilized for buffers. pH is equal to pKa plus the log of drop the acid, A minus goes on top. In this particular case, it's pKa plus the log of acetate, which is CH3COO minus, divided by acetic acid, CH3COOH. All right, so pH is equal to, what is the formula for pKa? What's the formula for power of something? It's minus the log of something. Here, that something is Ka. Okay, so make sure you know this for the exam. Also, make sure you know this for the exam as well. So pH is minus the log of Ka plus the log of acetate over acetic acid. All right, let's plug in some numbers here. Minus the log. Okay, this I'll give you the Ka on the test, on any exam. 1.5 times 10 to the minus 5 plus the log. What is acetate ion? 0.3. Everyone see that? 0.3 molar. What is the acetic acid? 0.2 molar. And this will give us the answer to this buffer. Okay, why am I calling this a buffer? Because I have two things here. I have the acid and I have its conjugate, so it's a buffer. All right, let's see if I can do this in one fell swoop. Minus the log of 1.75 times 10 to the minus 5 is that. Okay, plus log 0.30 divided by 0.20. That's one and a half, or 1.5. 4.93 is the answer. Okay. So let me just double check this here. Minus log. So minus the log of that is positive, plus just double checking. You know, I'm not very confident in my calculator things. 4.93. Okay. Yeah. So make sure you know how to do this on the calculator. That's all. All right. I think that's it for today's class. Thanks for coming. And today we talked about buffers, Henderson-Hasselbalch, and the common ion effect. Wednesday we'll talk about titrations. Okay, this will be used for your lab problems. All right, have a good day.